So we're going to change gears slightly now and look at something called quantifiers. Quantifiers are a way of taking open sentences and turning them into statements. And such they're very, very important. They help us get at some more interesting statements for us to prove and open up some problems and definitely can make some interesting things. So let's take a look. So let's go back to some open sentences. So here's a good example. The number x squared is non-negative. And of course the truth value of this statement depends on exactly where we grab x from. So for example, if x is a real number, this is true. If x is an integer, this is true. If x is an imaginary number, this is false. So because its truth value depends exactly on what x is, it's an open sentence. But we can prove it to be true for all real x. There's a little bit of extra text here for all real x as an example of a quantifier. So in that case, our statement would become, for every x in the real numbers, the number x squared is non-negative. And we saw this as a fact earlier in the course. So again, this extra bit of text, it has the effect of adding scope to a problem. It tells us where are we pulling this variable from? What are the values we're allowed to put into this thing? Okay? So it's an example of a quantifier. It takes an open sentence and turns it into a statement. Okay. So let's do some more examples. So consider the open sentence, x squared minus 5x plus 4 equals 0. They're used to thinking this as an equation, but it's really an open sentence. It's true or false depending on the value of x. So for example, p of 0 is false because 0 minus 5 times 0 plus 4 is 4, which isn't 0. So p of 0 is false. On the other hand, p of 1 minus 5 plus 4, 1 minus 5 minus 4 plus 4 is 0. So that's true. P of 2 is false, and so on. Now we don't really want to summarize things like this. This gets very tedious and isn't very enlightening, especially if we're pulling x from an infinite set. But we do need to decide what values we're allowed to put in. So what set are we pulling x from? So for example, we could consider the truth values of p of x over the set S, which is just 0, 1, 2, 3, 4. And we could summarize the results. We could summarize the truth tables by saying p of 1 and p of 4 are true, but 0, 2, and 3 make p of x false. And again, this is sort of fine if the set of values is very small or finite, but it really isn't going to work very well if the set is big or infinite. Now, we can summarize what's going on here using quantifiers by noting that p of x is true for some values of x, but p of x is not true for all values of x. And this little bit of extra text here for some and for all are quantifiers, and indeed they're the quantifiers that we're going to be studying in this course. So let's define them carefully. The universal and existential quantifiers. Now these are very grand sounding names, but we'll get used to them pretty quickly. So in particular, the universal quantifier, which is denoted by this upside down A symbol, is read as for all or for every. And it takes an open sentence p of x, for all x in A, p of x. This is a true statement, so it's turned from an open sentence by adding that quantifier here. It's turned into a statement. This is true provided p of x is true for every single x we pull out of A, and otherwise it's false. The twin to this is the existential quantifier. So the existential quantifier, which is denoted with this backwards E, is read as there exists. So again, we can take our open sentence p of x and turn it into a statement by adding this there exists x in A, so that p of x. This is true when we can find at least one value of x in A that makes it true. So we don't need it to be true all the time, we just need it to be true once for one value of x taken from A. And if we can't do that, it's false. So our example that we had on the previous slide becomes the following. There exists x in A such that x squared minus 5x plus 4 is 0. That's a true statement. On the other hand, if we say for all x pulled from this set S, x squared minus 5x plus 4 is 0, we know that to be a false statement because it's not true for every single x. Now notice we have a little bit of punctuation in here. We have a comma and we have this such that, so that, st. These are just little bits of punctuation. They separate the stuff going on in the quantifier from our open sentence. They're there to help the reader distinguish, okay, that's the quantifier and that's the sentence. Okay, it just separates the two. So it's punctuation, please do put it in. It really helps the person reading what you're doing. So let's do some examples. So here's an existential statement. So there exists n in the set of integers so that 7n minus 6 divided by 3 is an integer. Okay, and this is true. We could set n equals 3, and then the numerator becomes 7 times 3, 21, minus 6, which is 15, divided by 3 is 5, and 5 is an integer. So now notice, we can demonstrate that this is true by just showing one single value that makes it true. That there exists the existential quantifier, we just need to find one example that makes it true. And then it's a true statement. Let's look at the next one. For all n in z, so for all integers n squared plus 1 is a natural number. So this is another true statement. So we let n be any integer. Indeed, we have to show that this is true for every single integer. So generally, working with universal quantifiers is a little bit harder because we've got to make sure it works true generically, that it works for every single instance. Whereas an existential quantifier is a bit easier, and I have to show it true once. So let n be any integer, then, well, we know that n squared is an integer, so n squared plus 1 is an integer. Further, because n is real, we know that n squared is not negative, so n squared plus 1 is definitely bigger than or equal to 1. So it's bigger than or equal to 1 and an integer, so it's got to be a natural number. So again, usually working with universal quantifiers is a bit harder because we've got to show it's true for everything. So we've got to show it's true generically. We can't show it's true for a particular value, it has to work everywhere. So note, again, to hammer this point home, you cannot prove universal quantifiers using examples. Okay. So let's look at false versions of these things. So for all integers n, 7n minus 6 divided by 3 is an integer. Now this is false. This is false, and to see that it's false, we just need to show it goes wrong once. Because remember, in order for this to be true, it's got to be true for every single n. So we can just pick n equals 1, then the numerator becomes 7 minus 6 divided by 3, which is a third, and a third is definitely not an integer. So again, to show a universal quantifier is false, we just need one value that makes it false. Let's look at the next one. There exists n in z so that minus n squared is an integer. Now this is false. So we know the square of anything is going to be bigger than or equal to 0. So when we multiply by minus 1, we're definitely getting something that's 0 or negative. And that's all we really need to write out. So this is false. Let n be any integer. Then since n is a real number, we know that n squared is bigger than 0. So we know that minus n squared is less than 0. The natural numbers only contain positive things, so minus n squared definitely isn't in there. Now, notice, this is only going to be true if we can find at least one example that makes it true. So in order to show it's false, we have to show it's false everywhere, for generic element of that set. We can't just show it's false once, we have to show it's false everywhere. So it's generally a bit harder. So you cannot disprove existential quantifiers using examples. Now, just a little bit more before I finish this video. Quantifiers can be read in many different ways. We express them very differently in spoken and written English. And this can sometimes be a bit confusing, a bit problematic, so it's good to get a little bit of practice. So let's look at the existential quantifier. There exists x in S so that P of x is true. And I can automatically see on my slides that I made a small error. So I'm going to erase that and write A. So there exists x in A so that P of x is true. There exists x in A so that P of x is true. We can also read that as there is at least one x in A so that P of x is true. P of x is true for at least one value of x from A. We can find x in A so that P of x is true. We can choose x in A so that P of x is true. There is always one that makes it true. Okay, so it can be read in a lot of different ways. Now I can see I've made the same error on my slide, so I'm going to correct that again. There exists x in A, for all x in A, P of x. So for all x in A, P of x is true. For every x in A, P of x is true. No matter which x of A we choose, P of x is true. Every choice of x in A makes P of x true. Okay, so there's different ways of saying the same thing in English. And there's one more I want to write down and draw your attention to, which is very important. If X is pulled from the set A, then P of X holds. Okay? So if X is in A, P of X must be true. Okay? So this implication is an important way of reading that universal quantifier.